classes we were discussing this continuity in topological spaces. Okay, so just wait for 2-3 minutes because some students are still joining. Then I will start. So let us recall. See, I already explained you the definition of continuous function in topological spaces. And also we have seen that whatever we have studied in calculus and analysis so far, all those are particular cases of this definition. So as per definition, just let me quickly recall this definition. A function is said to be continuous. Suppose x and y are two topological spaces. Script x equipped with topology script t and y equipped with topology script set t dash. Then any function f is said to be continuous if whatever open set you will choose here, I mean with respect to this topology, its inverse image, set theoretic inverse image should be open in X. I mean, that should be a member of the topology present on X. See, so this one is the definition. If for each open subset V of Y, the set F inverse V is open subset of X. Just wait whether I have put this call on lecture on record or not. So this is definition of function to be continuous. And you can also see that, see the set theoretic inverse, this already I explained in detail that set theoretic inverse of any set is the set of all points of the domain for which fx belongs to V. And we will see that, see, set theoretic inverse of any set can be empty even the set V is non-empty. But we will see that in case of direct image, I mean f of V will never be empty unless V is empty. So for that, I need to recall some basics from the set theory. I will come to that one. And similarly, if there is a subset of X, sorry, okay. This also I explained how to interpret definition of a function to be continuous in terms of basis and in terms of sub basis. So all this I have explained. I just refer to my earlier lecture. Yes, to do this theorem 18.1. Look, if x and y are topological spaces and f from x to y be a map, then the following are equivalent. I mean, if f is continuous, then for every subset A of x, for every subset A of x here, if f of a closure will be always contained into closure of fa. F of a closure will be always contained to closure of fa. And for every closed subset, for every closed set B of y, the set F inverse B is closed in X. So you can also interpret your definition in terms of closed set. Okay, that whenever whatever closed set we will choose in Y, its inverse image should be always closed here. If this happens, then set is said to be continuous. Then function is said to be continuous. And this one is the definition in terms of neighborhood, that for each x belonging to x and each neighborhood V of fx, there is a neighborhood U of x such that f of u is contained into V. So to do theorem 18.1, we need to basically see in this, the proof is given in very short notation. So it for better understanding, we need to recall some results from the basics of set theory. I mean, whether this containment is there or equality sign is there, to understand all this, because without revising this proof seems easy, but it's not so one. I mean, you have to recall all those basics from set theory. Once you know, this proof is very easy. So for that, I need to we need to revisit the basics of set theory, which I will explain in short. And then after coming to it, we will look at this one. See, there is another result, result 18.2, how to construct continuous function, and then we will come to homeomorphism. Now, for this, just wait. Okay, in your book of topology by J.R. Munkres, just recall the basics from set theory. We already know that how to define a function. I am not going in detail of all this. We know that a function f is a rule which assigns, suppose this one is a non-empty set A and this one is a non-empty set B. So this is a rule which assigns every element of A a unique image in set B. And every element of this set A should be mapped. If there is at least one element which is not mapped, then this will not be a function. So first of important thing is that every element of set A must have image. Okay. And second, the image in B must be unique. I mean, more than two or more than one element may have the same image, this one is possible, but this one is not possible, that an element has more than one images. So this one is not possible. So already all these things you know, and you can also interpret in this form that if A is mapped to, if here we have an element A, then its image will be denoted by here f of A. So you can also use, I mean, interpret in this
तो
format.
ऐड कर लीजिए,
ठीक है ना? तो आप लोग यहाँ से ये रिवाइज कर लेंगे. एंड दिस सी image of A under F, that is FA is called image of A under F. I mean, ठीक है, तो ये सब है. See, and the second important result, very basic, you already know that by changing domain and codomain. See, once it become function, we will call this input, at which F is defined as A, and this one is called domain. This input is called domain in mathematical term, and this one is set B is called codomain, and the values at which it takes, at all the values of domain, that collection is called range. So range will be always, I mean, either it will be a proper subset of B or it will may be equal to B, depending on the nature of function. I mean, once the function is onto, so it will be equal to the set B. So that is depending on what I want to say here. See, this one, that very important thing is that by changing domain and codomain, you can construct different functions. You can see this function fx equal to x square, gx, these are not same function. Why? Two functions are said to be equal if they take the same values. So you can see that here the first map f is from R to R given by, and in second case we have changed the domain. I mean, we have restricted the domain to R plus, I mean 0 to infinity. So this one now becomes a different function. In the third case, we have restricted the codomain. In fourth case, we have both restricted domain and codomain. So all these are, by restricting domain and codomain, all these are different functions. They are not same functions. So that is what you can visualize here. So, and later on we will see that how to do restriction of functions on any set. So if f is map from R to R, then its restriction, we have restricted domain, and we have obtained another function g from R plus to R. So you can see that in the first case there is no restriction, and the mapping fx equal to x square, it's squaring x, so it will be symmetric about y axis. So you can see that you have this definition of parabola, I mean graph of this parabola, in which there you have whole R, and look, this R you will make on this one, and the codomain R on this axis. So you can see that this map is not 1, 1. Okay, because why? Because for to x we have the same y. So this map is not 1, 1. But if I restrict the domain, I mean, look at, have taken the from 0 to infinity, I mean R plus. So now only this portion will remain, and this map is 1, 1. But it's not onto y, because the negative real number have no pre-images. Negative real number have no pre-image. You can look this graph, if you draw a line parallel to say x-axis below, I mean related to any point, any negative real number, then it will never going to intersect this curve. So this mapping is not onto but 1, 1. Similarly, this one is okay. This one is 1, 1. I mean not 1, 1 but onto, because it is taking every values of this R plus. So whatever positive real non-negative real number we have always pre-images. Okay, and this one, see, this one is 1, 1 as well as onto. So you can see that by changing domain and codomain, the nature of function changes, and you have obtained different type of functions. So I am not going in detail, because already I will share you my video lecture in which this concept I have discussed in detail. Here just I want to recall. So look here what is written, that restricting the domain of a function and changing its range are two ways of forming a new function from the old one. And another way you already know, by taking composition of two functions. So that is the rule here. If f and g are, I mean, function defined from f from a to b and g from b to c, then f composition g and g composition f is defined in this way. So I will come to it later on. So remember that Yes. And this definition, a function f from a to b is said to be injective or one-to-one if for each pair of distinct points of a, I mean, whenever fa is equal to fa dash, this must imply that a is equal to a dash, or its converse, that if a is not equal to a dash, this implies their images should not be equal. Their images should not be equal. So either you can express in this way or this way. So this already you know. And for surjective, your onto, this is also called as onto. So for this, what will happen, that if f from a to b is a surjective map, then whatever y you will choose here, there must be some x such that fx equal to y. I mean, every element of codomain must be mapped, must have pre-image in A. Okay, so if you take any B from this B, there must be at least one A at which once you operate F, you will get this B. So this is the definition of onto. And for invertible, a function is said to be invertible if it is bijective. But remember the notation for set theoretic inverse, for set existence of set theoretic inverse, we don't require function to be 1, 1 onto, I mean bijective. Even function is not bijective, but one can also find it the set theoretic inverse of any set. So this is the, and this you already, okay. Now recall this, how to see, if f is a map from A to B and A naught is any subset of A, then f of A naught, I mean images of A naught, is defined as collection of all those B here. I mean images of, suppose we have A here and let us take its subset A naught. So if you operate f on this set, then we have here all those B such that B can be written as B equal to f of a for at least one A belonging to A naught. So this one is the definition of image of a set A naught. And this definition, pre-image or set theoretic inverse or inverse image, in different books you will find with different name, that already I explained in previous lecture in detail. That f inverse B naught is collection of all those A such that its image is in this set B naught. So this is the difference. So remember, whenever A belongs to f inverse B naught, I can say from here I can say that whenever A belongs to f inverse of B naught, this implies that f of A belongs to B naught. We will use it at several places. In fact, this result is like this. See, whenever f A belongs to B naught, this implies A belongs to f inverse of B naught. But observe that here nowhere we have written that for existence of set theoretic inverse function need to be 1, 1 and 1, 2. ठीक है ना? तो ये definition आप बिल्कुल clear करके रख लो कि notation हम ऐसे use करते हैं, but avoid confusion. Don't mix it with inverse of function. I mean, function is said to be invertible, invertibility of function. So, and you can see that there may be no points of A of A. I have already given you an example in which even set theoretic inverse image can be empty if B naught is non-empty. But in case of direct images, f of A naught will never be empty unless A naught is empty. So this is the difference. So that is what written here, that f inverse B naught can be empty even if B naught is not empty. So earlier I have already given you I have explained this one by example in the previous lecture. So just offset theoretic inverse. So just visit there. There I have already emphasized on this point that f inverse set theoretic inverse can be empty even if B naught is not empty. Now, so there are some very important points given here. What I want to say here, actually, okay, just read this. If f from A to B is bijective and B naught is subset of B naught is some subset of B here. So you can look the set theoretic inverse and inverse. It may be the set theoretic inverse of B naught, or it may be the inverse of a function from B to A. So for both we are using the same notation, but they are different. Now question is that, yes, this one. Suppose f is a mapping from A to B. We will do proof of this one. Suppose f is a mapping from A to B, and A naught is subset of A here and B naught is subset of B here. Then what can you say about A naught, whether A naught is contained into f inverse f of A naught? I mean, take the direct image of A naught under f and then it set, this will be a set, and take its set theoretic inverse, then what will be the relation between A naught and F inverse of F of A naught? And then, and once you obtain set theoretic inverse of B naught, set theoretic of B naught will be subset of A, and then again operate F of A. So you will find that this will be subset of B naught. And equality, you will see that we will see that the first inclusion is an equality if F is injective. So in case of direct images, we need to be careful. The first inclusion is an equality if F is injective, and the second equality, here you will get equality if F is onto, if F is onto. So not always we have equality here. Remember, this one is a very important point that people used to write, that F inverse of F of A naught equal to A. This is not possible always, and this is not possible. Yes, if F is your 1-1 function, then F inverse F of A naught is equal to A naught, and F of F inverse B naught equal to B naught. Otherwise, we have to follow this notation. And remember, in this book, this notation is used for this one. So we will see proof of this one. So because that this important point we will require in the proof of proving continuous function by different techniques. So you can see that here this example is given, and already I have explained this one with the help of similar example in the earlier lecture. So I'm not going to discuss it in detail here. But there are these three part. I mean, these are very important, and we will do the proof of all these one by one. So let me first recall this important point. If F from A to B is a map, and suppose A naught is contained into A and B naught is a subset of B, show that A naught is subset of F inverse F of A naught, and the equality holds if F is injective. And show that F of F inverse B naught is contained, and that equality holds if F is surjective or onto. And second result, that if F is a mapping from A to B, and suppose AI's are subset of A and BI's are subset of B for I equal to 0 and I equal to 1. I mean, A naught and B naught, A naught A1 and B naught B1 are subset of B, and A naught A1 are subset of A. Show that F preserves, show that F inverse, actually here there is a printing mistake. Show that set theoretic inverse preserves inclusion, unions, intersection, and difference. Preserves means you will get equality. I mean, the same notation will be preserved. I mean, suppose B naught is contained into B1. Then once you operate F inverse, then again inclusion. This is also called as inclusion. Then you will find that F inverse B naught, same notation here. F inverse B naught is contained into F inverse B1. So under set theoretic inverse, everything is preserved. I mean, F inverse B naught union B1 is equal to F inverse B naught union F inverse of B1. So you will get, in all other cases, you will get equality sign. So we used to say that if set theoretic inverse behave nicely, because we will get, I mean, in inclusion, again, the same sign is maintained. And in whether you operate it on union of two sets, this one is also true for, I mean, arbitrary intersection and union. And F inverse of B naught intersection B1, again you will get equality sign. F inverse of B naught minus B1, or say B naught intersection B1 complement, again this one will be equal to this one. But this is not always true in case of direct images. Remember that direct images always preserves inclusion and union only. This direct image only preserves inclusion and unions only. We will do its proof one by one. I will discuss at least 2-3 cases from each one, and rest you can take it as home assignment. So you can see that inclusion is preserved in, remember that inclusion is preserved under direct images. I mean, if A naught is subset of A1, then F of A naught will be also subset of F of A1. And also it is true, I mean, it behaves nicely on union, that F of A naught union A1 equal to F of A naught union F of A1. But in case of intersection, direct images not behave nicely. I mean, you will not, it's not always that you will get equality sign. F of A naught intersection A1 will be subset of F of A naught intersection F of A1. I mean, you may get equality here, or it may be a proper subset. So we will look at some examples here to counter this, I mean, to counter equality claim, and show that equality holds if F is injective. And again, F of this relation, that F of A naught minus F of A1 will be subset of F of A naught minus A1, or you can write it as A naught intersection A1 complement. Okay, so this is what I want to tell you, that don't ignore these basics. There are differences. You can always not write equality, just like and always in case of F direct images, we need to be careful. In the case of set theoretic inverse, it's okay. Everywhere you will get this one. and there is one, yes, this result show that B, C, F and G of exercise 2 holds for arbitrary union and intersection. Look here, this is also true for arbitrary union and intersection B, C, F and G. Look here, B, C, I said this, that this is also true for their arbitrary union and arbitrary intersection, and F and G, I mean this. Okay, now I am going to discuss the proof of some of them and some counter examples to discard equality side, and rest you can do. ठीक है, क्योंकि अक्सर होता क्या ना कि हम इन चीज़ों को छोड़ देते हैं और इन्हें बहुत बेसिक समझ के, और जो प्रूफ है ना वहाँ पे बहुत प्रॉब्लम क्रिएट होगी अगर आप इन चीज़ों को सीरियसली नहीं लेंगे तो। ठीक है, एक मिनट। अच्छा, एक काम करेंगे, अगर आपकी अगली क्लास होगी ना तो बीच में लीव कर देंगे आप लोग, मैं रिकॉर्डेड वीडियोस आपको शेयर कर दूंगा। इसी एक कंटिन्यूएशन में मैं कुछ स्टैंडर्ड रिजल्ट कराने जा रहा हूँ और आप लोग इसको देखिए। देखो, ये सब बेसिक आप जानते हो। वी से यूज्ड टू से दैट ए इज सबसेट ऑफ बी। एक्चुअली इन दिस बुक वी आर यूजिंग दिस वन, आई मीन फॉर दिस वन, एंड it will be used for this one. Okay, so whenever I write this, I mean this one. So A is subset of B. See, we say that A is a subset of B, or that B is a superset of A if every element of A is an element of B. I mean, for every x belonging to A implies x belongs to B. So in this case we will say that B is superset of A or A is subset of B. Okay, or A is, in some books you will find that A is contained in B or B contains A, or A is included in B or B includes A. So this notation you all. ठीक, अब देखो यहाँ पे जो मैं पहले आपको रिकॉल करा दूं कुछ इंपॉर्टेंट डेफिनेशंस। And we already know that one can also write A by B as, हालांकि देखो ये आप ग्रेजुएशन में पढ़ चुके हो, पर फिर भी मुझे लगता है कि बेटर अंडरस्टैंडिंग के लिए आपको थोड़ा सा एक शॉर्ट में रिकॉल करना जरूरी है। एंड वन कैन राइट A by B। आप मालूम है ना कि A by B कैसे, A minus B कैसे डिफाइन करते हैं? A minus B, A minus B is collection or difference of A minus B। हाँ, A minus B ऐसे लिखते हैं और A by B भी ऐसे लिखते हैं, ये दोनों नोटेशन यूज करते हैं। So A minus B is basically collection of all those x such that x belongs to A and x is not, but x is not in set B। तो ये आप इसे लिखते हो। A union B कैसे लिखते हैं? A union B is collection of all those x such that x belongs to A or x belongs to B। ये सब बेसिक आप जानते हो, मैं जस्ट एक शॉर्ट में लिख रहा हूँ। And A intersection B is all those x such that x belongs to A and x belongs to B। ठीक है ना, तो यहाँ तक कोई डाउट नहीं है। Now my question is that, say x belongs to A complement. If I say that x belongs to A complement, this implies that x is not in A, or in other words I can say that if x is not in A, this means x must be member of A, its complement। ठीक है ना, और ये हम मालूम है कि A by B को या A minus B को इस तरह भी लिखते हैं, A intersection B complement। Now the important result, second important result is that, see, let A and B are two sets, then my claim is that if A is contained into B implies B complement will be contained into A complement। कोई डाउट तो नहीं यहाँ पे? A is contained into B implies B complement is contained into A complement।
सर रिवर्स हो जाता
है ना, रिवर्स हो जाता है। कॉम्प्लीमेंट की प्रॉपर्टी पढ़े हो। एंड okay, this one, and second, these are some important result which you need to know, because actually under set theoretic inverse and direct images we are going to do all those proofs. So for that you need to require all these basic definition, and A intersection B equal to phi if and only if A is contained into B complement, और इट इज इक्वल टू सेइंग दैट बी इज कंटेंट इनटू ए कॉम्प्लीमेंट। देखो ये दोनों बहुत इंपॉर्टेंट रिजल्ट, बहुत बेसिक है, जो हम अक्सर यूज करते हैं। एंड यू कैन सी, जस्ट फर्स्ट ट्राई टू ऑब्जर्व इट फ्रॉम द ज्योमेट्री एंड देन लेट अस कम टू इट्स प्रूफ। So you can see that if A and B are any two sets, if A and B are any two set, either disjoint or A contain into B. So in the second case, you can see that if A and B, these two are independent. I mean, this is in second case, if you look at the second case, suppose A intersection B is empty, then you can say that this A is contained into B complement. B complement will be this portion. I mean this one. So you can see that set A is contained into the complement of B, or similarly you can say that B is contained into complement of A. So that is what I have written here, that if A and B are disjoint, then it is equivalent to saying that A is contained into B complement, or B is contained into A complement. And if A is contained into B, if suppose this is A and this one is B, and if A is contained into B, then it is equivalent to saying that B complement, look at B complement. B complement will be this one. Just to have a B complement will be this one. And A complement will be this one. So clearly B complement is contained into A complement. Is this clear to everyone? You can prove it also.
Yes.
How to prove? See, to show that A is equal to B, what is the technique we use to follow? Show that A is contained into B and B is contained into A. So to show A is contained into B, we start from here, that for every x belonging to A, show that x belongs to B. This is the technique. So to show that B complement is contained to A complement, what you will do, if you want to prove it, I mean mathematically, so let x belongs to B complement. So use this definition that if x belongs to A complement, then this implies that x is not in A. So you can say that x is not in B. Okay, x is not in. If x belongs to B complement, this implies x is not in B. We need to show that then x is not in A. So if you discarded B from the bigger set, and which is containing A, so if x is not in B, then obviously x will not be in A. Just look at, see, suppose this one is B and this one is your A. So if x is not in B, then obviously it will not be in A. So this is clear, yes, that x will not be in A also. So from here you can say that x belongs to A complement. आ गया proof?
Yes, sir.
तो बिल्कुल सेट थ्योरी का बेसिक है। अब मैं हर एक प्रूफ को नहीं कराने जा रहा हूँ, क्योंकि ये बहुत एलिमेंट्री चीजें हैं, इसमें टाइम वेस्ट होता है। आप लोगों को ऑलरेडी बीएससी में सेट थ्योरी पढ़ाया गया है, देयर यू हैव स्टडीड ऑल दिस, बट सम ऑफ द इंपॉर्टेंट ऑब्जर्वेशन in case of direct images and set theoretic inverse, that I need to recall. Those are very important because we may have studied there, but in topology that will be used at several places. ठीक है ना? तो ये सब उसी तरह से आप इन सब प्रूफ को भी कर सकते हो, खुद से ट्राई कर लेना, मैं बस उन रिजल्ट को आपको रिकॉल करा रहा हूँ। ठीक है, नाउ सो इन जनरल आई कैन से दैट, लुक, दैट यूनियन ऑफ AI, अगर आप आर्बिट्री यूनियन, सपोज I बिलोंग्स टू इंडेक्स सेट, सपोज AI इज आर फैमिली ऑफ सबसेट्स ऑफ X, I belongs to index set. I mean this index set can be finite, can be countably infinite, can be uncountable. So in general, suppose AI are family of subsets of X, where I is an arbitrary set, then the union of the sets AI is defined as collection of all those X belonging to X such that X belongs to AI for at least one I belongs to I. ठीक है ना? तो ये हमेशा हम यूज करते हैं, आपने देखा भी होगा कई जगह मैंने प्रूफ में यूज किया, फॉर एटलीस्ट फॉर वन आई, एटलीस्ट।
सर,
यस
सर नेक्स्ट क्लास की लिंक आ गई है।
ठीक है, आप लोग लीव कर दें, मैं रिकॉर्डेड क्लास आपको भेज दूंगा। एंड इंटरसेक्शन ऑफ AI इज डिफाइंड एज X belongs to X, X belongs to AI for all I belongs to I. Remember here the notation, for all and at least for one. Okay, so this is the definition of union and intersection. So we have seen that आप लोग की अगली क्लास है, आप लोग ज्वाइन कर लें, मैं रिकॉर्डेड क्लासेस अपलोड कर दूंगा। अब ये एलिमेंट्री है तो इसको वेस्ट टाइम करने की जरूरत नहीं है, लेकिन इसको रिवाइज कर लेंगे जरूर आप लोग, ठीक है। So we know that the image or range of A denoted by FA is defined to be, so already we have seen this one. This is basically collection of all those fx such that x belongs to A. Okay, and set theoretic inverse image or the pre-image, set theoretic inverse. Wait. So set theoretic inverse it is also known by the name inverse image or pre-image. This one is denoted by F inverse B, and F inverse B we have already seen that it is collection of all those x such that fx belongs to B. Okay. Now using this notation, see, already I explained that this also implies that x belongs to, whenever x belongs to F inverse B, see, whenever x is a member of F inverse B, this implies that fx belongs to B. Fx belongs to B. So we need to remember this one. I mean, it will be used at several places. And from here, we can interpret that from the direct images, I mean, from image or say range set, that whenever y belongs to FA, say, suppose y is some member of FA, suppose y is some member of the range set or say the image of A, this implies that there always some x from the set A at which this y will be obtained. There exists at least one x from A such that fx equal to y, ठीक है ना। तो ये दोनों इंटरप्रिटेशन हमें याद रखना है। जब भी y f of a का मेंबर होगा, y I mean y whenever y belongs to f of a, then this will hold, and I mean this is true. Or one can say that if there exists x belongs to such that fx equal to y, then y will be member of f of a. And in case of set theoretic inverse, this relation, these two are of this relation. Now using this, and another important observation here, you can see that suppose f is a mapping from x to y. Suppose f is a mapping from x to y, and b is subset of f of x, and suppose b is subset of f of x, I mean the range set. Suppose b is subset of range set, then remember, then only f inverse of b will be non-empty if and only if b is non-empty. Otherwise, it may happen that f inverse of b will be empty. If f inverse of b may be empty even if b is non-empty. So that I will. Now look at let us look at the proof of the points which I have discussed from the book of topology by J.R. Munkres, and let us do some of the questions from that. So for that, in that the first question is, so using all this, So we know that, let me first recall this one. See, x belongs to, whenever I say x belongs to A union B, this implies that x belongs to A or x belongs to B. Okay. And whenever I say x belongs to A intersection B, so we will use, we already know all this. Let me just, I'm writing here that we will write x belongs to A, and because in all those to prove set theoretic results and set theoretic inverse and direct images result, we require all this. And whenever I say x is not in A union B, this implies that x is not in A and x is not in B. So union will act like intersection, and whenever we have their negation. So, and look, and whenever I say x is not in A intersection B, this implies x is not in A और x is not in B. ठीक है ना, तो हम इसे यूज करेंगे. अब एक काम करते हैं, तो पहला रिजल्ट करते हैं इसमें. Suppose AIs are subset. Suppose AIs are families of subset of X, where I belongs to index set. These are subsets of X. Now I need to show that the direct image is the result. Let me first do it for direct image result. That union of AIs, I mean for arbitrary, where I belongs to index set, if we take its image under F, then it will be, I mean in case of union we will get equality. It will be equal to union of F of AIs, union of F of AI, where I belongs to index set. So in case of equality, direct images behaves nicely. I mean, we will get equality. So how to prove this? How to prove this? So the proof is, I mean, this is very similar. Just we need to use the set theoretic result. So for that, I can say that, see, let us start from C. To show that A is contained into B, we used to take Y belongs to A, and for every Y belongs to A, show that Y belongs to B. So let us start, take a Y here and show that it is lies in their union. So this is the algo. Now let Y belongs to F of union of AI, where I belongs to, say, index set. So we already know that, see, whenever Y belongs to F of union of AI, so just use the definition of direct images, F of union of AI, F of AI. So there must exist X. Look at this proof, look at this definition. See, when you say that Y belongs to F of A, this implies there exists X from the set A such that Fx equal to Y. So just use this definition. Proof is very simple. So if I say that Y belongs to F of U union of AI, this means there must exist some X from union of AI such that Y will be attained at F of that element. So let me write here, there exists X belonging to union of AI. Right here always I belongs to index set such that Y is equal to F of X. This one is by definition. See, all these things are related to definition. Now use this one. When X belongs to union of AI, just use this one. When I say that X belongs to union of AI, X belongs to union of means X will belongs to at least for one I. So use this step. So X belongs to union of AI means X will belongs to at least one of AI. So I can say from here that, actually this is also true, that there must exist some I from index set such that X belongs to AI for at least one I, and at that Y must be equal to F of X. there exists I belongs to I such that x belongs to I and y is equal to f of x. Okay. Now you can also use, see this one, say whenever y is equal to fx, see I can also say that there exists I belongs to index set such that y belongs to f of ai. Actually this x is coming from ai, so you can also write that y belongs to f of ai, because f of ai will be collection of all those images where x belongs to ai. So y in, if you replace this x by the whole set ai, then y will be the member of this f of ai. And recall, whenever I say y belongs to f of ai, this means that y must be the member of their union, I mean union of f of ai. There exists I belongs to I such that y belongs to fi. So just use this definition. See, if union of ai is collection of all those x belongs to such that x belongs to at least one of ai. So if x belongs to ai set, then it must be union of all those sets. So here in our case, y belongs to f of ai. So I can write that y belongs to union of f of ai, where I belongs to index C. ठीक है ना? तो ये एक प्रूफ मैंने करा दिया. आप इस तरह से प्रोसीड कर सकते हो. सेम इज द ट्रू इन केस ऑफ इंटरसेक्शन. Sorry, I mean you can, but in case of intersection we will not get equality, we will get one-sided containment relation. So to claim that in general in case of intersection we don't have equality, let me discuss this one. So you can approach in the same way. But to claim that, see, if in case of intersection, you can see that f of a intersection b, in case of direct images, f of a intersection b is not always equal to f of a intersection f of b. I mean, you will get equality on one-sided, but I'm not going to prove that in general you will get that f of a intersection b will be contained into f a intersection f of b. So to make a counter claim, you can use this technique. Say, you can think of functions like this one. Say, let us take f of x equal to x square. Under this, look at the direct images, and let us take a is equal to, say, minus infinity to 1 closed, and b is equal to 1 to infinity. B is equal to 1 to infinity. Then what will happen? Look at what will be f of a intersection b, and find f of a. Look at f of a intersection f of b. So under this map, f of x equal to x square. It's square in x, so it will be symmetric about y-axis. So just draw it. Okay, so this one is the function x square, and here we have 1. Suppose 1. At 1 we will get this value f of 1. Okay, at 1 we will get f of 1. So f of 1 is basically 1 here. So you can think of this one. I mean, what will be f of a intersection b? What is common in, see, a intersection b is equal to 1, is it? Clearly, the only point common in a and b is a intersection b is 1. Now at 1, what value we are getting? At 1, we are getting the value as 1. So I can say that f of a intersection b is equal to f of 1, and f of 1 is 1. F of 1 is 1. Actually, this is a set, so its images will be a set. So write in set form, and this is not equal to, say, 1 to infinity. Is it? 1 to infinity is basically what is your f a intersection fb. Look at f a intersection. Is it so? F of a intersection. Take a f of a. So f of a intersection. What will be f of a intersection b? You can look at f of a. I mean, f of a is minus infinity. A is minus infinity to 1. Minus infinity to 1. and f of a is its images. So it is going to take the values from 0 to infinity, 0 to infinity. And again, from here, you will get the images from 1 to infinity, images from 1 to infinity. So if you take their intersection, you will get from 1 to infinity, 1 to infinity, which is written here. So you can see that they are not equal. I mean, in general, f of a intersection b may not be equal to f a intersection f of b, but f of a intersection b will be contained into f a intersection fb. So this one is a counter example. In case of direct images, one need to be careful at while taking intersection. Equality sign may not be there. But if this function is, see, 1, 1, then clearly you will get equality here. So that is what. Now, let me discuss one more case of set theoretic inverse, and the rest you can do by your own. So we have seen that in case of set theoretic inverse, everywhere we will get equality. For example, let us show that, say, f inverse of union of bi. Suppose bi are subsets of family of subsets of x, where I belongs to index set. Then set theoretic inverse of their union will be equal to union of set theoretic inverse of bi's, where I belongs to index set. So union of set theoretic inverse. I mean, you will always get equality sign. How? So again, to prove this, see, to prove a equal to b, you need to show a is contained to b and b is contained into a. So you have to do the both parts. So let us start from this one. See, okay. So let x belongs to f inverse union of b now. Let x belongs to f inverse union of bi's, where bi's are family of subsets of x. I belongs to index set. So f inverse of union of bi, where I belongs to index set. So just use the definition of set theoretic inverse. This means, look at here, what I have used, that whenever, say, in case of f inverse b, if x belongs to f inverse b, then fx must belongs to b. So we need to follow this definition, that whenever x belongs to f inverse b, then fx must belongs to this b. Fx must belongs to b. So use this definition here. The proof is very simple. X belongs to f inverse union of bi. This implies fx belongs to union of bi. And whenever something is in union, then it must be in one of the bi's. I mean, there must exist at least one index I belonging to index set, such that fx belongs to at least one of bi's, at least one of bi. And now, see, if fx belongs to bi, fx belongs to bi, so I can also write in this way that there exists I belonging to I, such that x belongs to f inverse of bi. Again, set theoretic inverse, because we need to write into this format. So just use, because this result is true both sided. Whenever x belongs to f inverse bi, you can write fx belongs to bi. Just use the definition of set theoretic inverse image of set bi here. So these two are equivalent. So I have written x belongs to f. And see, if x belongs to f inverse bi, then x will be in their union. So I can also write here that x belongs to union of f inverse of bi, where I belongs to index set. Okay, so in this way, similar thing will work in case of intersection and all that. I'm not going to do all those. Just in all other cases, even in case of equality, you will get sorry. But here, in another important example which I want to discuss is the case of what will happen if we take this one. Now this one, see, we need to show that f of f inverse b, take first set theoretic inverse of the set b and then operate its image, direct image f on this one. So for that, I need to show that suppose f is a map from x to y. Let me write here completely. Suppose f is a map from x to y, and a and ai, I mean, are subsets of x, and b and bi's are subsets of y. Then we need to show that, see, f of f inverse b will be contained into b. This one first, and if we take, and what about this one? I mean, what about this one? F of f inverse b. F of f inverse b. Will, question is, will b be contained into this one? If not, then we need to give a counter example. And second, with a, claim is that a is contained into f inverse of f of a. A is contained into, I mean, first take direct image of a, and then take inverse image of that set f of a, and we will prove that a will be always contained into f inverse of f of a. And what about its converse? I mean, whether this f inverse f of a, whether this will be contained into a. So if not, then we need to give a counter example. So for this, okay. So let us do first one, how to show this containment relation. So let, suppose y belongs to f of f inverse of b, set theoretic direct images of set theoretic inverse of b. So as per definition, if y belongs to f of f inverse b, so there must exist some x. Just use the definition of direct image. There exists some x belonging to f inverse b, such that y is equal to fx. Actually, we are using here this definition. This one, see, whenever y belongs to f of a, there must exist at least one x from the set A such that fx equal to y. So that is what I am using here. So if y belongs to f of this, so there must exist some x belonging to f inverse b such that y is equal to fx. So this implies that y, and y is equal to fx. See, although b, because b is collection of all those fx. Now, yes, this implies y is equal to fx. This implies that y is equal to fx belongs to b. Now, what about its reverse inclusion? What about its reverse inclusion? I mean, the reverse inclusion is not always true. The reverse is not always true. How? So for a counter example, one can consider function on any say 2-point set. Let me take this one. See, let us take f from 0, 1 to 0, 1. This function. Okay, such that f of 0 is equal to f of 1 is equal to 0. I mean, at 0 and 1, function is taking value 0. Now look at the first, take the set theoretic inverse of set B. So for this, if we consider, let B is equal to this one, B is equal to 0, 1. ठीक है, देखो क्या किया. Suppose B is this 0, 1. ठीक है. Suppose B is this set 0, 1. Then what will be f of B? You can see that f of B will be 0 because f of B is collection of all those elements at which the f takes the values on B. So there are only two elements, 0 and 1 in set B, and at 0 it is also going to be giving us 0 and 1. The image of 1 is also 1. So in f of B is basically collection of all those images. So that is 0 only. F of B is 0 only. Okay. Now look, f of b is 0 here. And what I need to show? I need to show that the reverse equality is not true. So you can see that b is the set, this one 0, 1, and we have obtained f of b. Now look at f inverse b. F of b is 0. So first of all, we need to find f inverse b and then take its f. So for that, f inverse b, if you recall that, then f inverse of b, set theoretic inverse of the set b, is collection of all those elements belonging to 0, 1, I mean set 1, such that fx belongs to b. I mean fx belongs to this one, such that fx belongs to set b. This one is the definition. I mean all those elements from domain, collection of all those elements from domain whose images is inside B. So inside B there are only two elements 0 and 1. Now look at what are those elements at which fx belongs to B. So you can see that, see, I can write this one as x belongs to 0, 1, such that fx equal to 0. Actually there is only one image. I mean at all these x, we f is taking value 0 only, and 0 is obviously a member of 0, 1. So this is so basically 0. What is that? What are those x? Those x are 0 and 1 at which the images are in 0, 1. So that is the set B itself. So you can see that f inverse B is set B itself here. F inverse B is set B itself here, and thus you can see that f of f inverse B. I mean f of f inverse B is B, and f of B is singleton 0. See, f inverse B, let me write that, f inverse of B is B. So, and f inverse B, f of B. In place of f inverse B, I have written here B, and in place of f of B, we have proved it as 0, singleton 0. This set is 0, and you can see that singleton 0, that f of f inverse B, B is not contained into f of f inverse B. Why? Because B is the set 0, 1. So this 0, 1, that is the set B. This is not contained into 0. So in general, we don't have the reverse inclusion may not be true always. So this one is a very good example to understand this. And similarly, you can think of this one. Okay. So similarly, take it as home assignment and construct example here in this one. That A will be contained into f inverse of fa, but this inclusion is not true. Look at this function is not 1, 1, because at two values, at 0 and 1, we are getting 0. Okay. So now here I am going to end this lecture, and in next lecture, using all these results, I will do the continuity theorem. ठीक है, आप लोग रिवाइज कर लेंगे. कुछ रिजल्ट्स मैंने एक दो तो करा दिया, का आइडिया आपको दे दिया गया है. सेट थ्योरेटिक इनवर्स के ये रिजल्ट्स इंपॉर्टेंट है, एंड वी विल यूज इट एट सेवरल प्लेसेस इन व्हाइल स्टडीइंग टोपोलॉजी, जनरल टोपोलॉजी. ठीक है, तो कुछ मैंने रिजल्ट आपको एक आइडिया दे दिया है, कुछ मैंने छोड़ दिया, लेकिन वो इंपॉर्टेंट पॉइंट जो मुझे यूज करना वो मैंने आपको रिकॉल करा दिया है. ओके, वी विल मीट इन नेक्स्ट क्लास.